Today we're talking about fractions and proportional reasoning. That's what you're here for. All right, so with us is Susan Resnick, and I have a little bit of information about Susan. Susan has over 30 years of education experience as a math teacher, a special education teacher, a gifted and talented coordinator, a principal, a district math coordinator, and a national and international staff development for mathematics instruction. So she's kind of done it all. She works with passion to bring understanding about differentiation and the principles of good instructional practice to the world of math teaching. She works extensively with schools to implement mathematics curriculum from Singapore, and she is an author of the award-winning series Singapore Math Fact Fluency from Marshall Cavendish Education. Says the consulting author and TE author of Math in Focus 2020 edition and the U.S. Consulate for Primary Math 2022. That's a lot of stuff, Susan. I don't know how you keep
a lot of writing.
All right. So with that, I'm going to hand this over to Susan. If you have a question about anything, please put that in the chat for everybody. If anything about the presentation you have a question for, put that in to everyone. Everyone should be able to see that, including Susan, myself, and Kara. If you have a question specifically about Brainingcamp, I would ask that you change the setting to myself, Ryan Doherty, or Kara Rinn, and we will answer those on the side. But let's save the presentation stuff for everyone.
Awesome.
I think that's everything, right?
Yeah. All right. Let's get started. Okay, so we're going to warm up with a problem, which I always like to do. And here's the story. For a science experiment, Felipe found that the total distance that two crickets could jump was at most 4 5/6 feet. Each cricket jumped more than 2 feet, and cricket A jumped farther than cricket B. Your job is to figure out what are the possible distances covered by each cricket. And in order to do this, we're going to go into our first live session. So I am going to go over to Brainingcamp. You'll see that the crickets are not on here, but there is a reproduction of the number line. So this is the tool you're going to use. And I'm going to show you how to join my live session I'm just going to go share. And you'll see it says share live, so I'll do that. And all you're going to do is under the share code, you can put in GWF and PFJY. I will copy that and stick that into, for some reason, I still don't have everyone. So Ryan, you might have to stick that one in for me.
Thank you, Kara.
Awesome. I'm going to lock your activity just for a second while you guys are all getting in here, which means you won't be able to do anything until I unlock. Is there a limit on live, Ryan? How many people can get in?
No, there's not.
There is no limit.
Okay.
We've had a few hundred on there before.
Awesome. So far, I'm seeing 31. So while people are still joining, I'll just explain to you what you're seeing. So this is a newer feature of Brainingcamp just from the last year or so, where I can actually see everyone's screen. So if you're teaching in class, I can see every student's screen. And right now, my favorite new feature is that I can lock it, so nobody can do anything till I'm ready, which is really awesome. In a second here, I'm going to unlock. So wait till a few more people get in, and then I will unlock. All right, here we go. So hopefully, let me see here. Hopefully I'm going to put the story back up so you're all in there, I'm hoping, right? And here we go. Here's the story. So go ahead and start working. Actually going to copy that, I believe, into the story. I don't know why I didn't to begin with.
Susan, you have everyone locked.
Oh, they're still locked.
That's what someone just said.
Oh yeah. How about that? Unlock. There you go. Sorry about that.
Yep.
Now you should be able to work. Here's the clues again. All right, hopefully you have the clues. And I'll just give me a second there. So I am sending you the clues just in case you forgot. So hopefully you just got a message. Yes, Sarah, you'll see on this one, for some reason, I made a mistake and the story didn't show up, but you'll see on the future slides, the story is there. So I don't know what happened and with that one. So hopefully you got it in the message. I sent you a message and hopefully everyone got the clues there. Okay, so you guys can see, hopefully you can see my screen, that as a teacher, I can see what everyone is doing. And what's really cool about that is that I can kind of see what sort of methods we're getting at this point. All right, so I'm going to hop to slide 40 or 46 here. I don't know who this is exactly, but I'm going to load this so that you can all see. Hopefully that worked, or maybe not. Let's try that again. Part of my problem here is I have this open twice. Let's see. Okay. And that just went.
Are you trying to see the thumbnail, Susan?
Yeah, I don't know where it just disappeared.
Hit the little participants button at the top where it says 74.
Yeah, it's weird.
And it'll pop back up.
It just never loaded for you.
Yeah, it never loaded.
There you go.
But it's still not loading. I don't know why. Strange. I've never had that happen.
I've never seen it either.
Let's try a different one and just see if it's something weird. There we go. I don't know, but it was about that screen that was strange. Okay, so here's someone who's starting to think about how they might reason, and I think they were just starting to get used to the tools themselves. And you guys can see that there's different ways that we can show 1/6 on here, right? We can show it through a block. We can show it through a jump. We can actually also show it through an arrow, which is another way to kind of look at the interval. And we can see that we have the end line or the goal here of 4 and 5, 6. So that's interesting way to start thinking about it. Let's take a look at one more here. Oops, I think I might have pushed it out to all of you guys instead. So now you should all have that one. Interesting. Let's see. I don't know, it's acting a little bit odd today. There we go. Okay. Yeah, there we go. So someone
46 was using an iPad and
it wasn't pushing. Okay. So so you guys can see here that this person thought about that B would have made it to 2 and 1/6, and then A would have completed the rest of the distance. Okay, so hopefully you guys can see that. And you can see some different ways to think about this problem. But let's go back to why we were even talking about this problem in the first place. So one of the things that I want you to think about is this is kind of our end goal, is to get here, or to get to a student who can think about the fractions in this sort of flexible way. We have lots of restraints here. We know that we're going to have to add two fractions to end up in a mixed number. We have to think about being able to compare fractions here. We have to think about, is there more than one possible answer actually to this question, or is there only one possible answer? So this is kind of our end goal. This is where we're hoping to end up today, is that all of our students by sixth grade, sixth grade would be able to answer a question that has this degree of difficulty. So let's start to talk about, like, how does that happen, or how do we build that understanding? Okay, so I just want to start by talking about, like, what is the trajectory for building fractions? And fractions really start in the US anyway, and I know we have a lot of international people here, but in the US, really, it really starts in first grade, but I started in second. It starts in first grade really with just partitioning shapes equally. And by second grade, we have what I call understanding fractions, and then we have fluency with fractions. So when we're talking about the understanding standards, all second grade has is understanding standards. And in fact, they occur under geometry, there is no separate strand for fractions in second grade. And the only role for a second grader is to understand the language of fractions. In fact, they do not need to know the symbolic form of fractions. They just need to understand partitioning a shape into equal parts. And we'll talk a little bit more about what that might look like. By third grade, then we start to add the symbolic form or the notation for fractions. And really our goal, again, is understanding, and especially unit fractions, although we also introduce non-unit fractions. And we introduce the idea of fractions to make a whole. And at that point, we want to really focus heavily on comparing fractions. By fourth grade, then we're working on equivalence. And we're looking at how do we find equivalent fractions, both through multiplication and through division, and also addition and subtraction of fractions with like denominators, and how to multiply a fraction by a whole number, which is starting to get at proportional reasoning. So we'll talk a little bit more about that important transition. By fifth grade, then, students should be completely fluent with addition and subtraction of fractions by the end of the year with unlike denominators, and be able to develop an understanding. So here's where we start to see that difference between fluency and understanding of multiplication of fractions and division of fractions in limited cases. And what we mean by that is just unit fractions for the most part, divided by a whole number, or a whole number divided by a unit fraction. In sixth grade, then, we start to connect ratio and rate to fractions and work heavily on understanding division of fractions. So we're going to sort of move through that trajectory. We'll revisit this again at the end if you didn't catch it. And we'll be able to see how we did talking about all of these topics. Okay, so I want you to just in a minute, take a second to think for yourself. And I want you to just type in the chat, what does that mean in second grade when they say to understand fractional language? What does that mean to you? Good. Lots of people talking about parts of a whole, breaking a whole into smaller parts, critical vocabulary. Good. Halves, thirds, and fourths. Good. Fractional language. Excellent. Equal parts. Nice. Divide, divide, divide. Excellent. Yeah, fraction is division, which actually, interestingly enough, doesn't really come up until fifth grade, fraction as division as a topic. So they need to sort of have the concept of that in second grade, but honestly, the formal notation of that doesn't come into place until fifth grade. Okay, excellent. The phrases. We're going to talk a lot about using the language. Okay, so I want you just to take a look at this picture and type in the chat something you see, just anything you see. How could you describe something from this picture? Nice. The pink is a half. Some people see 4 parts. Good. Yellow is a 1/4. Okay. Yellow is a 1/4. Another way to say that. Excellent. Different size pieces. Circle with colors. I love that, Laura. I definitely have kids. That's what they would have said. Pinky is half. Good. Okay, so we can see 2 different ways. Somebody said they see 2 different ways to describe a half. Interesting. Okay. Anybody notice anything maybe about like the green and the red? Somebody said the red is they think it's a 1/3 of the green. Green and red together might make another 1/4. Good. Green, yellow, and red make another half. So do you see how, like, without any fractions at all, we have no fractions on this page, you could tell me quite a bit of fractional language, right? And I think your kids can do the same. Even a kindergartner could usually tell me that the pink is half of the circle, right? Even if they don't know anything about fractions, they are able to do that. So that's really the kinds of conversations that we want to start fractional language with no symbols at all. We're just talking about different pictures, and let's talk about that a little bit more. So I want you to think about this picture now. Which of these figures are cut into equal parts? Which ones are cut into equal parts? Okay, so for most people, it's easy for us as adults, right, to see that A is cut into equal parts. But which ones do you think the kids might struggle with? And I see most people, a lot of people didn't pick C. Let's talk about C for a second. Is that equal parts? What do you think? Yeah, everybody's saying yes. But is it always equal parts in a triangle if I do it that way? No, how come? Because it only works with an equilateral triangle, right? Only if the sides were equal to begin with. And so that's another like really interesting thing to think about. I'm always thinking about opportunities for extension, right? Well, there's a great opportunity for extension because not all triangles can be divided into thirds that way, right? But some can. Okay, interesting. So people are saying they think E is hard to see. Would you guys agree? Yeah, E doesn't look equal, does it? They don't look like equal parts. Could we prove that they are in fact equal parts? We definitely can, right? Okay. Excellent. Okay, so this is the kind of language that we're going to start to use in 2nd grade without having to introduce the symbolic notation. Let's look at another example here. Okay, we're going to go back to a live session. Hopefully it works this time. And your question is to decide which of these shapes are divided into halves. What you're going to see when you get in there is that these arrows move. Do you see? So you're going to just choose the arrow and put them where you think they go. So I'm going to give you another live code. So here you go. Oh, now I've got everyone. Thanks, whoever fixed that. There you go. Live code's in the chat. It's also on screen. Go ahead and join again. See if you can manipulate this one. There you go. All right, so this time, all you have to do is move the arrow to choose the ones that you think are divided into halves. Excellent. I can see all of my students' work. So I see people saying this one and whoops, and this one. Oh, my little arrows locked there. This one and this one and this one. Excellent. Okay. So the reason I wanted to do this activity now is I want to have a conversation about halves. Okay. So you told me that all of them could be called halves. I want you to think about this. All right. You told me that this is a half, these are halves, these are halves, these are halves, and these are halves. So I have a question for you. Are the halves, and I'm just going to pull a couple of these off, in the circle, is this half this equal to this half? You're calling them both by the same name. Is this half equal to this half? What do you think? A lot of people are saying no. Okay, two fundamental understandings of fractions we're going to talk about today, and that is one of them, right? Is that we cannot compare halves unless the whole was the same. Now, I want you to think about that because their whole life, we've been telling them that 2 is equal to 2 is equal to 2, and it doesn't matter if it's vertical or horizontal, or if I put the 2 in a domino pattern, it's still 2, right? But all of a sudden, I'm telling the kids, there's this new kind of number called a fraction. And 1/2 is not always equal to 1/2. Now, that doesn't sound like that big of a deal, but in reality, that's a really big sort of brain explosion to think about, that 1/2 is not always equal to 1/2. I have to think about the whole. Okay. Additionally, is this half, these are both the same shape. Is this half equal to this half? What do you think? No. Because not only does it have to be the same shape, but it has to be the same size. That right there in a nutshell is second grade. Okay. That's the one thing they have to understand. They have to understand that the shapes have to be the same size and the same shape, and the parts have to be equal, right? That's it. That's all of second grade. If they can do that, they've done it. Okay, so let's go back to the presentation. Let's talk a little bit more about that. So we might consider giving kids some problems like this. Which shapes show fourths? This is sort of similar to the one that we looked at with halves, although this time they are all divided into 4 pieces, right? So some students might have a misunderstanding or a misconception that if it's 4 pieces, it's automatically fourths, right? So we might try some things like this with them. And then, like I said, we have this big fundamental understanding in second grade that the wholes need to be the same size and the same shape in order to compare their parts. Okay. And I want to talk for a second about why is this so confusing to kids? And let's just do a very simple example. What is 2 plus 3? Go ahead and put that in the chat. It's not a trick question. 2 plus 3 is 5, right? Okay. All right. Now, what is 2 10s and 3 1s? What does that make? What does that make? Excellent. 23, good. Okay, everybody's good so far. 2 plus 3 is 5. 2 10s and 3 1s is 23. We're all feeling really strong. How would you describe this picture? What is 2 cats and 3 dogs? You see what you had to do there? All of a sudden, we got 2 animals or 5 pets or 5 animals, right? Some people are going right to fraction language and saying 2/5 of them are cats or 3/5 of them are dogs. So what's so interesting here is we had to do something that we only have to do in fractions, which is we had to give them a new last name, right? We had to come up with a new last name. We couldn't call them cats. We couldn't call them dogs. We have to call them animals or pets. This is the key behind renaming fractions later on, right? In terms of finding a common denominator, okay? So what we're getting at here is that the denominator in Latin means of the name. D means of, nom means name of the name, right? A denominator, all a denominator tells us, like fifths, is the last name of the fraction. That's all it tells us, okay? And so we need to think about that in terms of when we're helping students understand equivalency. So we're going to get at that. What I'm really trying to get at today is that when we understand the why behind fractions, the how, which is what we all sort of get caught up in, becomes really, really easy to understand, okay? If we don't understand the why, the how is not easy, all right? So we're going to take a look at how does this develop. So we start with students in addition models, right? And this is from Baruti. He says that, we should be thinking about addition models sort of like this. If we see 7 here, right? One way to make 7 is to think about it as 4 and 3, right? All right. And then I can start to look at some other ways to make 7. I could say, well, not only is it 4 and 3, not only is it 4 and 3, but it's also, oh, my slide won't work. So sorry about that. But there's other ways I could do it. I could do 5 and 2. I could do 6 and 1, right? So there's lots of ways that I could decompose 7 into different shapes, right? And then we get to multiplication and we start to tell the kids, okay, well, let's think about this. How might you describe this picture, right? It's how would you describe this picture if you want to put that in the chat really quick? 3 groups of 5, right? All right. And in reality, we're using equal groups now. So we're moving towards fractions, right? But it's still repeated addition. Okay. And even if we look at it this way, what do you see now? You still see 3 groups of 5, right? Or 3 rows of 5, maybe, even when we're looking at a array model, but still, we're still thinking about repeated addition of equal groups. Okay. And now I'm going to show something that a bunch of 3rd grade teachers are going to get mad, but here we go. What does this one show you? Oops, not that one, but this one. What does that show you? Now people are saying 5 groups of 3. Okay, but some of the 3rd grade teachers are probably getting a little bit mad at me because they always like the groups to go this way. What I love about this model, which is used in Singapore, is that we're not rotating the array. We're not saying that in order to have 3 5s, we have to rotate the array. Here we have 5 3s. We can use the same directionality of the array, but we think about the groups in a different way. This is why the commutative property works, right? Because it's the same array. We didn't have to tilt it, right? But we can look at the groups in different ways. Okay, but either way, we're still looking at repeated addition. And honestly, even when we go to the bar model, okay, we are still looking at equal groups or repeated addition. All right, excellent. So all of these are still repeated addition. We're moving sort of towards fractional thinking because we're moving to equal groups. We're thinking about equal parts, but we're going to talk for a minute about how this is just a little bit different than fractional thinking, because what happens now when we look at fraction bars? How does that feel different to you than looking at those addition models? How does that feel different to you? Good. Some people said that the 1 is remaining constant. Now we're looking at parts of the same whole. Excellent. Okay, good. And so you can see that the wholes getting smaller and smaller and smaller. Do you start to see any equivalencies here? Anybody seeing anything that's equivalent? Good. Everything's equivalent to 1. That's true. So now I can see that it took 2 halves to make 1 or 3/3 to make 1. A really important part of 2nd and 3rd grade. Okay, excellent. Okay. But I can also see, good, somebody said, I can also see that 2 pinks is equal to 4 yellows, right? Excellent. Okay. And if I look really carefully, I can see that 5 purples are also equal to the same thing. Okay. All of this language that we're having so far, we haven't looked at the symbol. We've never used the fraction symbol so far. Okay. Super interesting, right? To start to think about how can we build this language and build this understanding without introducing the symbol at all yet. Okay. All right, so what we're doing when we're moving from whole numbers to fractions is we're moving from this idea of decomposing or taking a larger number and breaking it into smaller parts to what we call partitioning, where we're actually dividing. Okay, so we're really moving from an addition subtraction sort of model with whole numbers, multiplication as repeated addition, to a fractional model where we're talking about partitioning. And if you haven't thought about it in that way, it's kind of important to think about that we're moving between those 2 concepts. So I'm going to have an activity for you so you can kind of feel what that feels like to move from decomposition to partitioning. So we're going to try one more live session. Here you go. Actually, as a matter of fact, I'm not going to do this one as a live session because it's got a lot on it. So what we're going to do on this one is you're just going to go to your own screen through the share code, which I will throw in the chat. There you go. So you can mess around with it just a little bit more than we can do. So remember, again, you just go to share code button, drop it in there. And as you're doing these, I just want you to work through this number string really quick, and then we'll talk about it. So I'll be quiet for just a second. So Chris asked, when you use the term partitioning, does it always imply equal parts? Yes. And that's the difference between decomposing and partitioning. Decomposing, I can take a 6 and make it 3 and 3 or 4 and 2. But when I'm partitioning, the parts have to be equal. All right, so I'm just gonna, you might still be working, but I just wanna talk through this a little bit. You notice that I created a blue answer box over on the right so that you could put your answers in there. It wasn't very specific about the instructions. So some people might have just taken this 1/3 and 1/6 and dumped that right in the answer box, right? But because we are talking about, excuse me, partitioning, what I was hoping is that you might use your 6th pieces to notice here that those fit perfectly into that 1/3. And so 1/3 and 1/6 is really the same as 3 of these 1/6 pieces, which then I could name 3/6, right? Okay. So that one, we started with equal parts and just putting equal parts together. The number string here is that then I'm going to give you a larger fraction, right? 1/3, and say, can you still give me an answer just in 1/6 pieces, which you were able to do. Okay, so now we look at 1/12 and 1/6, and I want to think about, can you give me answers in 1/6 pieces? And it doesn't work so well, right? It doesn't work that well on this one because in fact, I only have 1/12. If I had 2/12, which we have on the next one, I could have done that, but on this one I can't. So this time my answer, instead of being in 6, is probably going to have to take the name of the smaller fraction, right? So now I can say if I have 1/12 and 2 more 12ths, which is what I can fit in that 6th. Now I have a new answer of 3/12. Okay, interesting. All right, and why did that happen? Because I couldn't build a 6th out of these 12ths, right? But I could go I couldn't build a 12th out of the 6. I had to go the other direction. Okay, this one's interesting because there's actually 2 correct answers, right? I could have gone to 12ths. I could have said, oh, okay, there's 4 of those 12ths, right? I could have put 2 in the 6th, or I could have said, oh, I could have built it out of just 6, and that's kind of interesting to think about because, in fact, 2/6 is equal to 4/12. So that's kind of a more flexible answer. Okay, and I'm just going to put these over here so they're out of my way. And then I've got one where now all of a sudden I have to think about 3 fractions and building that understanding. So this is something that's really important in Singapore math, which is this idea of layering these problems correctly and in the right order to build understanding. So I want you to just take a minute in the chat and just write like what happened to you as you worked through that sequence. And when Jenny just wrote something interesting, so I'm sorry, I started reading that and let me finish my sentence. Right, what happened to you as you started working through that series of problems, and how did that change your thinking, or how did your thinking develop as you played around with those fraction pieces? Nice. Yeah, I think I love what Linda just said, which is like it forced you in a way, right, to find equivalent fractions, to say like they have to all be the same pieces, or it's helpful if they're all the same pieces to make the addition work. And I could have given you that direction, right? But we didn't ever introduce an addition sign. We're still using the language of and makes, right? We sort of loosely introduced the symbol, but really the pieces are what's guiding us, not seeing the 1/6 or whatever. So I want you guys to think about, like, how do we design these kind of thinking? Someone said, what about a kid who saw these as a third? That's super interesting. Like what about the third is interesting? How would you help kids like experience that? Okay. So I think, as we layer these problems carefully, we can help kids have these like deeper understandings. All right. So, we start to build the understanding of addition here without introducing the symbol. Now we're going to introduce the symbol, right? So we can start to think about writing addition and subtraction sentence for picture. Now, what did you see here? You saw 1 out of 2 parts and 1 out of 2 parts shaded, and altogether that makes 2 out of 2 parts, right? Same thing here. And this one has a little bit of a stretch now because the shading doesn't match, right? So it's not like we're showing the first box and the second box, right? That would be easy to see that it formed the 2/3. But in this case, now the students have to be flexible enough to see that even if the first piece is shaded in both, that creates 2 shaded pieces, even though they might not be in the position they are in the answer, okay? And then here we're now looking at subtraction. If we have this one and we take away a shaded piece, what's the result of that? And so we can start to have students recognize addition and subtraction sentences, which is different than asking them to produce them themselves as we think through that. Okay, so from that, then we might move to the number line. And one of the things that I find students really struggle with is this transition to the number line. And there's a couple of reasons why. It's very, very abstract. They tend to forget that the 1/3 is actually the tick mark that we use for 1/3 is actually showing the end of the interval. Does that make sense? So just like with whole numbers, when we have a 1 or a 2 here, it's actually showing the distance from 0 to 1 or 0 to 2. Here, when we show 1/3 or 2/3, we're actually showing the distance from 0, right? And students lose that understanding often as soon as we go to the number line, and they think that this tick mark's name is 1/3 or this tick mark's name is 2/3. And so it's really important that before we move them to the number line, we actually transition them by putting the interval pieces or the bar model pieces right on top of the number line. And we show them that the number line is truly just a measurement model where we're measuring the end of this piece and marking the end of this piece. So I just want you to understand that like right there is where a lot of kids start to lose their understanding when we go the number line too early because it's too abstract. All right, so we're going to try another problem that I want you to think about. And this time I'm going to have you choose, so you can get into Brainingcamp, choose any pieces you want. Okay, so there's the bars, there's the circles. You can do this any way you want. And here's the situation. Amy and Adam each order a small personal pan pizza of the same size. Amy ate 3 equal pieces of her pizza, and Adam ate 4 equal pieces of his pizza. Amy says that they ate the same amount. Is that possible? How? So go ahead. You pick your tool this time. I happen to use this one, so if you want the problem, I will send you the share code. And that way you'll have the problem on the thing. Hold on for a second. Okay, if you came up with one solution, see if you can come up with another. If you have not ever used the fraction, I am in the fraction ring tool. It's under fractions. And if you go to the lower right-hand corner, you'll see that there's this toggle. So when you get in, you're on basic, basically. When you toggle now, you can go to the rings. You'll see. Do you see? Okay, there you go. And so the way these work is you can put a piece in and you can start looking at equivalency. So I know Amy ate 2 pieces, I suppose. Or did I do 3 in the other problem? I might have done 3. I might have changed the problem on you. No, 2. Okay. So Amy ate 2 pieces, right? So I can see that. And I can prove that Adam ate all 4, and that was the same thing. So I can prove that 2 halves was the same as 4/4. Another way I could have done that is just actually by looking at the rings themselves. So I can see that 1, 2, 3/4, and then I can actually manipulate this if I want to change the parts. So you might mess around with this. This is one of my favorite tools here because we can start to see equivalency that way. Yeah, I think in the other problem I had 3 and 4 parts, so you can do it either way. This is the easier one, 2 and 4 parts. 3 and 4 makes it a little bit harder. So lots of people saw that they could have eaten the whole pizza, right? Are there any other ways that they could have eaten the same amount? Anybody able to figure out another way? Okay, Amy can only eat 2 pieces though. So if Amy ate 2/4, right? Then Adam had to eat 4 pieces. What would he have eaten then? Nice. Adam could have eaten 4/8. Okay. So people are saying Amy could have eaten 2/3. We can check that one out. Let's see. See what happens if Amy ate 2/3. Adam would have eaten 4/6. Let's see if that's the same thing. I'm gonna have to rotate my. Sorry, I've got a lot going on here with. So if you pull this, do you see that? I can rotate that over there. Let's see if that's the same thing. So do you see how I'm able to sort of change my thinking by using the rotation tool? Excellent. So 2/3 was the same as 4/6. Interesting. Okay, excellent. So this kind of tool now also gives me the necessity to create equal fractions, right? Or to think about equivalency, because I'm doing a problem. And actually, apparently I changed my mind from 3/4 to 2/4. I think 3/4 is harder, a little bit harder, the 3 and 4 pieces than the 2 and the 4, to show equivalency. So lots of tools we can use in Brainingcamp. We could use the fraction strips, we could have used the fraction circles, we can use the ring, but all of those things help us get at that idea about equivalency. So let's take a look at another problem. This is from one of the textbooks that I wrote. And I want you to just, this is tricky, actually. I did this with Mark when we were getting ready for the training, and we had a really great conversation about it. So I want you to just think about which of these models is showing the sum of 1/2 and 1/7. Only one of the 3 models, and the other 2 are incorrect, and see if you can figure out why. Go ahead and put your reflections in the chat. Oops, sorry, didn't mean to change it on you. This Google Slides thing is, there we go. What do you guys think? Which one's correct? Any ideas, sir? There we go. Okay, I'm seeing model 3, model 2. So there's a little bit split here between 3 and 2. Okay. Okay, interesting. Okay, so model 1, I think everybody can kind of see, although I do think model 1 is the one a lot of kids would pick, honestly. They see a half, or they think it's a half, and they see a 7th, and they're just like, that's the answer, right? But it is hard to choose between model 1 and model 2 and model 3. And this is what I want you to think about. Model 2 is showing 1/7 of 1/2. Does that make sense? 1/7 of the half. Model 3 is showing 1/7 of the whole. Interesting. Okay. So if a student can understand this, they really understand equivalency of fractions. Okay. There's a great problem to talk to the kids about, because I think it really gets you to start thinking about, well, this does show a 7th. It does, but it's only showing a 7th of the half. And you're going to see why that's going to be important in a minute as we move towards ratios. Okay. And so this is a key understanding now, and we only have we have about 10 minutes. So I think we'll get through this, but we're moving now from thinking about the fraction of a whole, the fraction of a one whole to the fraction of an entire set. Okay. And that's where that's a big transition for kids. It happens around 4th grade. We're moving out of this idea of that a fraction only describes one part of one whole or several parts of one whole. And we have to think about that. One of my favorite things to do, honestly, is to use tangrams like these. Okay. So I just show that I have the kids build this thing and like build this picture, right? And they say, okay, what fraction of the whole is the blue piece? So I'm going to give you guys a second to see if you can visualize that. What fraction of the whole is just that blue piece? It's a little harder when you can't move them, but ooh, I'm getting lots of different answers. I love it. We have 3 different answers so far in the chat. Chris, you asked area or number of pieces. It's pretty much the same thing, I think. Okay, excellent. Question was, what fraction of the whole bunny is the blue piece? There you go. Okay, excellent. All right, excellent. Okay, we've got lots of different answers still. So like I said, it's much harder. We can't manipulate them, but most kids can, when they move them, they can figure out there's 2 in this sort of, in the parallelogram. There's, I think there's also 2 in the square. There's 3 in the smaller, like the medium-sized triangle, and then there's 4, I believe, in each of these. So you can add all of those up. Here's another one that I might do, very similar. What fraction of the whole thing is the blue square, right? And once kids have done a couple of these, they get pretty good at determining what fraction of the whole set is the colored piece. Okay, great thing to put in a center or rotation because kids can do it independently. All right. Okay, excellent. So, I love this. Somebody said, I saw this as 1 out of 7 pieces. Okay. And if we're talking about fractions, we have to talk about equal parts, right? So I might question them and say, well, okay, but if all the parts have to be equal, right? And we're talking about a fraction here, what fraction of the whole is blue, right? Okay, excellent. So I think the answer is 1/8 or 2/16. Okay, very good. Easy thing to set up for kids. All right. Well, how does that build into some higher level thinking? So we're gonna do sort of a difficult problem, and I'm not gonna have you do this one in Brainingcamp. I'm just gonna let you write this down. Ken had a number of colored marbles in a bag. 1/4 of his marbles were red, and 2/3 of the remaining marbles were blue, and the rest were yellow. Given that there were 120 red and yellow marbles together, how many marbles were in the bag? I'm going to just give you a moment of think time. Here's the problem again. Give you a little hint that you might start with a bar model that shows 1/4 of the marbles being red. Now, the reason this is interesting, right, is that we can't cut a marble in half. So we're not talking about 1/4 of a marble. We're talking about 1/4 of this whole set of marbles. Okay. All right. So let me walk you through this. So 1/4 of marbles are red. I think everyone can see that picture's pretty easy to see. Then 2/3 of the remaining are blue. So here's the remaining part, right? Okay, what was left over. 2/3 were blue and the rest are yellow. So now we sort of have this picture, and hopefully that's really easy for everyone to see. Now, the next part's the tricky part. It says, given that there were 120 red and yellow marbles together, so I'm going to just move this red piece over here, okay? And I know that that's equal to 120, which means the other half must also be equal to 120. And therefore, the whole thing is 240 marbles. Anybody Want to see that again really fast? I'll walk you through that one more time. 1/4 of the marbles are red. We're talking about the remaining marbles now. 2/3 of those are blue, and the rest are yellow, which means 1/4 was yellow. If I shift that red piece over here, I can see that there was 120 red and yellow together. That was 2 of the 4 units, which means that the total must be 240. Okay, I want you to think about what algebra, if you had to write the algebraic equation for this, what would you have written? Because for me, I go, huh? Like, I don't know. I don't actually know what the algebra would have been. And so what I want you to see is that these visuals make it so that I can access some really difficult, pretty difficult fractional problems, fraction of a set problems, right? By looking at the visual models, right? Okay. So I want you to think about that. Yeah, Elizabeth said it might have taken me a system. It might have actually, in a 3-part system, which would have been like a crazy thing to solve. Okay. All right. Excellent. So to kind of wrap it up, I just wanted to talk to you about, we won't go over into Brainingcamp because we're sort of losing some time, but or we're just at time, but I just want to talk about 6th grade for just a second and how we transition. So we've been talking about fraction of a set or fraction of a group of objects, right? And it's really easy for me to move that into ratio thinking, because here's a fraction of a set, right? And I could say that there are 16 squares in all, and 7 of the 16 are blue, right? So I could write a 7/16 are blue. Are red. And I could say that 9/16 are blue, right? Easy to describe that as a fraction. But it's also easy for me to describe this as a ratio. I can say that the ratio of 7 to of red to blue is 7 to 9, or I can say that the ratio of blue to red is 9 to 7, or I can say that the ratio of red to the whole, right, is 7 to 16. And so I can use the exact same images to start to move kids into thinking about ratios. So kind of as our final activity here, I want you to just write an answer to this question: how are a fraction and a ratio related? And thinking about this picture, I could talk about either fraction of a set, or I could talk about ratios. How do you see those two things as related? Excellent. They're all talking about parts to wholes. Good. Excellent. People are still working on the algebra. I love that. Okay, good. They're really the same thing, right? I mean, they're not exactly the same thing. I mean, normally when we talk about fractioning, we're talking about partitioning, and here we're talking about wholes to wholes typically, right? Parts to parts. So excellent. Okay. All right. So just to wrap up for today, we kind of walked ourselves through this trajectory, right? We talked about using fractional language. We talked about understanding a fraction and comparing unit fractions. We talked about equivalency. We talked about understanding the development of addition and subtraction in terms of being fluid. And then finally, we talked about that fraction of a set stuff. And at the very end there, we started to talk about comparing ratio and how does ratio relate to all of that fractional understanding. And so you guys, very good. You just went through 5 years of fractions instruction in an hour. So thanks so much for joining us. Any final questions? I also, Ryan, do you mind throwing in the chat the share codes for the?
Yeah. Yep. I was going to actually do that right now. A couple of comments that I had that related to one of them. All right, guys, hold on your chats for just 1 second. I'm going to put in a link right now that will get you. One of the things I was going to say is, at one point I wanted to take a screenshot of something that you were doing, Susan, and you switched it right as I was like, oh, I got to screenshot this.
Okay.
But Susan just shared with us this Google Doc that I just put in the chat that has all of her codes that she's used and all the things that she used to kind of put this presentation together. So if you want to go back up in the chat to where I just posted that, but there's a Google link there that you can go and get all that information, right? And then on our screen right now, here's some information that you might need to, if you wanted to contact any of us at Brainingcamp. Really simple email, support, info, and sales at Brainingcamp. And then you have Susan's email as well.